All right, moving into astronomy, we are now looking at light, and we're going to be using spectroscopy to make sense of what the light information is telling us. So where does light come from? And we've looked at this a couple times prior, but something that is emitting light, it's giving off heat as a result of an energy transfer, or it is reflected off of a surface. Most of us view light, right? Most of our world is viewed by light that is reflected. But that light has to come from somewhere. So it comes from somewhere, from something that is emitting light. So we're going to be studying stars, in particular our sun, as the generators of light. So light moves in straight lines that we're going to call rays, and they move in these bundles of energy called photons. And that each photon, right, whether red or blue, has a very specific defined quanta that it must abide by. It's kind of the rules. That red is red and blue is blue, and blue cannot become red and red cannot become blue. And when I look at this picture here, we need to make sure we realize that as the frequency is changing, so is the wavelength, that they are inversely related. That the higher the frequency, the smaller the wavelength. That at the end of the day, they are all forms of the electromagnetic spectrum, therefore they're all traveling at the speed of light. So the duality of light, is it a wave? Is it a particle? Well, it's actually both. Light can be described as a wave. Whether viewing the electromagnetic spectrum as a whole or only the visible light spectrum, we can see that light has a characteristic wavelength and frequency. So as the wavelength here is, we can say that this is a short wavelength. It is associated with a larger frequency. And therefore, if I consider, I'm going to have you consider blue at some wavelength. We can call it wavelength from this line here to this line here at a frequency of 640 hertz. Comparing that to red, a larger wavelength and a lower frequency. But light can also be described as a particle. Light can act like a stream of particles, tiny bullets fired from a gun simultaneously. When the photons strike an object, they impart their momentum onto the object, thus changing its momentum. So we can talk about solar sails. Solar sails are kind of the perfect example of that. A solar sail is simply a photon coming in, it hits it, it gets redirected, and the momentum is imparted onto the object or onto the solar sail itself. So each photon of light has its own momentum. The magnitude depends on the wavelength, but the direction is always in the direction that the photon is traveling. As the photon reflects off the sail, the direction of its momentum changes, and so the sail must experience a change in its momentum too. So a solar sail is a perfect example. If I shine light on this object, it's actually going to move. So we're using light to make sense as to how we view our universe. Astronomers use light to study the universe. Light is emitted by objects that are hot, like stars. Technologies, such as telescopes, allow us to see and study much more than we can see with our eyes standing on the Earth's surface. And by understanding the electromagnetic spectrum, we can determine what objects are made of based on the spectra we detect coming from an object. So we can study the light and make sense of it. And lastly, the Doppler effect is an apparent shift of light or sound, or any wave, as it is in motion. So we'll apply this. We'll use the Doppler effect to apply what happens to the apparent frequency as that light or sound source is in motion. So here's a cool picture. This is the Eagle Nebula picture taken from the Hubble Telescope. Appearing like a winged fairy tale creature poised on a pedestal, this object is actually a billowing tower of cold gas and dust rising in the Eagle Nebula. That the pillar is 9.5 light years in its height and its size, and 57 trillion miles. In this case, about twice the distance from our sun to the nearest star. Stars in the Eagle Nebula are born in clouds of cold hydrogen that reside in chaotic neighborhoods, where energy from the young star sculpts the landscape and the gas. The tower is like a giant star incubator for newborn stars. A torrent of ultraviolet light from a band of young stars is eroding the pillar and changing it. So as we view this as a cloud of dust and gas and debris in this nebula, we can actually view it kind of like a cloud that we would see in Earth's atmosphere. Over time, it's changing. It's evolving. There are different energies pushing and pulling and moving, and forces acting inward. And so it's changing over time. It's just really, really massive, and that time scale in which it changes is going to be on a little different time scale than a cloud would be changing on Earth. So that brings us to spectroscopy. So what is it? Well, it's the study of light. Spectroscopy is a very important tool in astronomy. Light is energy that moves through space and can be thought of as either waves or particles. The distances between peaks of waves of light are called the light's wavelength. Light is made up of many different wavelengths and frequencies. Spectrometers are instruments that spread out light into wavelengths, creating spectra. Astronomers can study spectral lines, which are the fingerprints of atoms and molecules. Each atom has a unique spacing of orbits and can emit or absorb only certain energies or wavelengths. This is why the location and spacing of the spectral lines is unique for each atom. Astronomers can learn a great deal about an object in space by studying its spectrum, such as its composition, what it's made of, its temperature, its density, its motion. Can be talking both rotation and how fast it's moving towards or away from us. So light is the key to studying the universe. So within the electromagnetic spectrum, we've talked about this in the past. Gamma rays, highest frequency, shortest wavelength. Then I move down as I move from right to left. We're decreasing frequency, we're increasing our wavelength. We're actually even decreasing our net energy, as energy is a function of the frequency. But so gamma, highest energy, highest frequency. X-rays a little bit less. UV, visible light. Infrared or heat. Microwave and radio waves, where radio waves have the longest wavelength and the lowest frequency. But we can treat the visible light spectrum just like we are treating the electromagnetic spectrum, whereas your blue, your violet end are going to have the highest frequency, they're going to have higher energy, and they're going to have smaller wavelengths than, say, the red and the orange end of the visible light spectrum. But all of these are traveling at the speed of light, c, in the vacuum of space, 186,282 miles per second. The electromagnetic spectrum to the left illustrates different forms of pure energy, whereas the visible light spectrum is breaking down visible light into its individual color components. So the best way to do this is to use telescopes. These are what are actually leaving Earth's atmosphere to study the light. So telescopes allow us to view tiny amounts of light from great distances. Light is a wave and carries information. Studying light, we study the characteristics of what produced it. Example, from stars. We can determine a heck of a lot just from studying the light from stars. So the Hubble Telescope is what we have used in what this video, I encourage you to check it out. It views space from space with no atmospheric interference. And what it does, it's going to take that incoming light and it's going to separate it into its individual components and be able to study what's going on within those individual components. So here's a prism. As white light enters the prism, it refracts. As it bends by changing its speed, it is separating it into its individual components. And this is where we get our Roy G. Biv colors. We're separating it into its individual characteristics. So experiments show that light has a duality to it, both wave properties and particle properties. As a wave, its motion can be characterized by its wavelength. As a particle, called photons, it can exert pressure on matter. But we're going to study the light, white light, as a part of the electromagnetic spectrum as we separate the white light into its color components. So we're looking at it in this case as a wave itself. So the individual components, red, orange, yellow, green, blue, and violet. And this is done using a prism. So a prism allows white light in, the light refracts as it changes its speed to the new medium, and it separates into the colors that we can see. Well, the process or the science of studying this light, once we've kind of separated into its components, is called spectroscopy. That there's different forms of light that we're going to be evaluating. We can look at the continuous spectrum. Here I have an incandescent bulb, right? It's hot, it's emitting light. It's going to be, if we separate its colors through a prism, it's going to get what's called a continuous spectrum. It is produced by an incandescent or glowing solid, liquid, or gas that's under high pressure. It contains a continuous band of wavelength, right? This is what we see. This is our continuous spectrum. It has all of these colors here. It consists of a continuous band of wavelength that is generated by a common 100-watt light bulb. This is what we are most commonly familiar to seeing. So this is our continuous spectrum. Well, here if I have the light that is traveling through this cooler gas and I refract it through the prism, I get something that's called this dark line spectrum. It's called the absorption spectrum. So dark line spectrum are absorption spectra as light passes through a comparatively cool gas at low pressure that are identified as missing wavelengths, right? The dark bands, the dark line spectrum, they're quote unquote missing this area of light, or missing these areas of wavelengths. These tell the composition of the object that's emitting the light. These lines are considered fingerprints as to the makeup of the object. As light passes through the star's atmosphere, right, in this case, the gas on the outer atmosphere, right, the gases on the outside are cooler than the gases on the inside. The energy is absorbed and then re-emitted. So you can actually determine by these dark bands, right, from the absorption spectra, which are also dark line spectra, you can determine the composition of what the gases within that star are made of. So we've looked at an incandescent bulb, we've looked at, so this is our continuous spectrum, we've looked at our absorption spectra. The last one is what we call a bright line or an emission spectra, where you actually are seeing bright lines, the emission itself. So bright line spectrum are emission spectral lines produced in hot or incandescent matter at low pressure. It is a series of bright lines that identify the temperature and the matter's composition as well. Emission spectra are produced by large interstellar clouds, right, nebula, consisting of hydrogen gas excited by extremely hot stars. So if I have this incandescent, this really hot gas, and I separate the colors within this prism, I'm going to get these bright line spectra, right, emission spectra, what's emitting the light. And these are going to be fingerprints. Just as these are dark line absorption spectra, these are going to be bright line emission spectra. So let's look at this one more time. Let's get it a little differently. So this is the continuous spectrum. Continuous spectra, also called thermal or black body spectra, are emitted by an object that radiates heat, right? It has some temperature. So the light is spread out into a continuous band, with every wavelength having some amount of radiation. For example, when sunlight is passed through a prism, its light is spread out into its colors, right? Roy-G bit. Or in the case of the picture here, we'd see it as your violet, or excuse me, in this picture up here, our continuous spectrum, as our violet, our blue, green, yellow, orange, and red. So it's just simply the colors in reverse. But let's look here at the absorption spectra of hydrogen. Right here, these lines right here, these dark lines are your absorption spectra. It has a tendency, it's viewed as being missing. Whereas here, these are my emission spectra, where we get these colors, these color signatures at these particular known frequencies, or in this case, wavelength. So if I look here, if I see this, if this is hydrogen, and I align this and I correspond this to some absorption spectral readout that I get, I can actually see if the wavelengths that are missing here, if they are consistent with the signature or the fingerprint for hydrogen, I can say very confidently that this material that is emitting light is emitting these spectral signatures of hydrogen. It must contain hydrogen. So when we look at sunlight, we're really looking at the absorption spectra, that the solar spectrum is a continuous spectrum of incandescent gas. Look closely and you'll also see fine dark lines crossing the solar spectrum. These lines are called Fraunhofer lines. The dark lines are produced by gas above the surface of the sun, from which absorbs some of the incandescent light from the sun below. Each of these lines is produced by one atom, or ion. However, several lines may be produced by one atom. Two lines close together in yellow are a famous pair of sodium lines, right? These two right here, kind of a pairing here, sodium pairing. So these are the absorption lines from our sun. So if I look here and say, okay, I've got these lines, these are great. Well, I can correlate these lines here to what I know of as different elements in these absorption spectra here. So these different elements have different fingerprints, right, at these different wavelengths. So I can then just correspond these here to what I know are in the absorption spectral signatures from our sun and say, well, our sun must have these elements within it. And then if I look at the absorption lines from a supercluster of galaxies from a billion light years away, and I start finding these signatures from that light, I can draw some very specific conclusions that these galaxies must contain the same elements that we find in our sun, and it contains these very specific elements that I have these fingerprints for. So once I start applying this to the Doppler effect, or I start applying the Doppler effect here, is if I have a light source that's stationary, that the waves radiating out from it are all going to be consistent. But if I put it in motion, something happens. That we can observe the Doppler effect by something that's going to change with the apparent wavelength. So if I take this light or a sound source, if a sound is coming towards me, it gets higher pitched. If a light is traveling towards us, it shifts towards the blue end. And if it's traveling away, the Doppler effect says it's going to be a larger wavelength. In the light, we're going to call that a red shift.